Hello everyone, my name is Morty and today I will present our paper, an in-depth investigation of Leo SNET's topology design parameters. This is a joint work with my coworker Zihan and my advisor Sangeetha. So let's start. Nowadays, Leo constellations are rapidly growing. As the video demo shown here, there are thousands of fast-moving Leo SNETs at hundreds kilometers altitude, providing internet service all over the world. Compared to terrestrial and geo SNET network, LEO SNET has high global coverage, reasonable speeds, lower latency, and also are cost-effective. Most importantly, LEO network supports a new advanced data transmission technology, the laser-based intersatnet link. So what is intersatnet link? It is a physical layer technology for transmitting data directly between SATnets using laser-based links. Here is an example image. Without ISLs, LEO constellations can only interact with the ground stations using a bandpipe topology. This requires high-cost ground stations across a large number of locations on the Earth. But now with ISLs, we can directly forward the data from source through multi-hops across LEO SATnets to the destination ground stations. This enables LEO companies to build fewer ground stations. LEO constellations are moving towards more ISLs usage in the future. Starlink already uses ISLs in regions like Alaska. Imagine that in the future, all SATnets could use ISLs to route data. Literally, it is a huge dynamic network. Our paper studied the performance of ISL-based topology under various configuration parameters. Like the plot shown here, LEO constellations have some key parameters, which forms the shape and determine the network performance. Altitude is the height of the SATnet from the Earth's surface. One constellation may have many shells. Each shell has multiple orbits around the Earth with different phase shift. Each orbit typically has the same number of SATnets evenly distributed. Inclination is the angle between the orbit plane and the equator, which determines the latitude one shell can cover. Here is a parameter table for three proposed commercial constellations. Different constellations has many different parameter shells. Here is a visualization for those shells, and you can see they has different density and coverage. We are curious about the logical guiding these parameter selections. What is the impact of these LEO shell configuration parameters on network performance? To explore this, we choose the simulation-based method to measure the performance of different LEO constellations with different parameters. The simulator we use called Hypatia, and the topology for ISLs is PlusGrid. The user traffic is the end-to-end traffic of 100 ground stations chosen on Earth. Each simulation simulates 400 seconds movement of the constellation, and every second we compute the shortest path for all ground stations pairs. Here is an example plot showing in one time step the shortest path between the Hill and the Brasilio through ISLs. Note that in this simulation, we do not account for any other real-world network factors like throughput. Here is a motivating example. We compare Starlink Shell 1 S1 with an example shell we designed by ourselves, E1. We keep all settings the same except for these three key parameters. Note that E1 has only half number of SATnets of S1. The latency performance is here. Y is the cumulative distribution where X is the max round-trip time between all 100 user endpoints during the 400 seconds simulation. Performance is better when the curve is more towards the left. You can see that the E1 performance is much better than S1, although it has only half number of SATnets, which is a little bit counterintuitive. Fewer SATnets, but have better latency performance. This highlights the impact of parameter settings. To investigate further, we designed two experiments to explore the magic of parameters. One is the synthetic configuration experiment. It is an ablation study about control variables. We varied each parameter independently while holding other constant. We generate synthetic shells with different number of orbits, number of SATnets per orbit, and the inclinations. Second experiment is a progressive experiment to understand the relationship of ground station's positions and the inclination. I will introduce more about this later. We use the two metrics to represent network latency performance. One is the geodesic slowdown, which compares the shortest path through ISLs to the ideal Euclidean path along the Earth's surface. Lower value suggesting paths closer to the ideal. Another one is the average hop count, which is the average number of hops to road data. Each hop in the ISL network involves handover time and potential data loss, so fewer hops indicate a more stable and efficient connection. Let us dive into detailed experiments on each parameters. When satnets per orbit increase, what will happen? On the x-axis, we have geodesic slowdown. The y-axis shows the CDF over all pairs of endpoints. The performance is better when the curve is more towards the left. We vary the satnet's orbit from 20 to 44 across fixed values for number of orbits. We show results for 20 and 33 orbits here. We have more detailed results in the paper. We observe that in all cases, as the number of satnets per orbit increase, the geodesic slowdown decreases. We also found a performance threshold of 28 satnets per orbit. Below this, network performance degrades significantly. When the number of orbits increases, what will happen? We again plot the cumulative distribution of geodesic slowdown while fixing the number of satnets per orbit. Performance is better when the curve is more towards the left. We observe that increasing the number of orbits generally results in decreasing geodesic slowdown. Again, we notice that when both the number of satnets per orbit and the number of orbits lower than 20, performance drops significantly. For the inclination, when the inclination is increasing, it is very hard to tell which one is better. Therefore, we designed the experiment 2 to further explore the magic hidden behind the inclination. To better understand the impact of inclination, I will introduce first the concept of geographic angle of user endpoints pairs. It is the angle between the equator and the plane that contains 3 points: the Earth's center, user endpoints A, and user endpoints B. Our intuition is that the alignment between satnet's orbit inclination and the geographic angle of user endpoints affects the constellation's latency performance. If the orbit inclination and the geographic angle between a user endpoint A and B are not aligned, the path is more likely to follow a zigzag pattern across multiple orbits. If the geographic angle is close to the inclination of the orbits, the shortest path is more likely to follow a single orbit for most of the distance. To prove this, we categorize user endpoints traffic into 9 groups based on their geographic angle. The interval is 10 degrees, and evaluate the network performance on the different inclination constellations. Here is a visualization of each group. We connect each user endpoints pairs using red line. The red line has different geographic angle. Here is the number of distribution of those pairs. Most of the user endpoints traffic are within 30 to 70 degrees. Here is the selective result of the average hop count for experiments 2. The y-axis is the number of average hop, and x is the 4 different constellations inclination. From left to right, you can see that 3 groups user endpoints pairs performance on the different inclination constellations. Lower points means better performance. As the right circle point out here, when the inclination aligns with the user endpoint's geographic angle, the performance is better. So summary of the results. First, for the parameter number of orbits and the number of satnets per orbit, there exist thresholds below which performance drops significantly. Second, beyond the threshold, there is marginal improvements in performance as satnet's density increases. Third, alignment of satnet's orbit inclination and the user endpoint's geographic angle can improve latency performance. Therefore, a suggestion for the newly planned LEO constellation: make sure the density of SASNets exists the threshold and tries to align the inclination of the constellation with the user endpoint's geographic angle you want to serve. For future work, future efforts could be put on studying alternative ISL topologies beyond the plus grid structure, analyzing the performance of combining multi-share configurations, and also consider congestion control or other real-world events during the simulation. Thanks.